A chemical equation is a shorthand way to describe a reaction that gives the formulas for all the reactants and the products. The reactants are what you start with, and the products are what you end up with.
A simple chemical equation is A plus B yields C plus D. A and B are the reactants, and C and D are the products.
Chemical equations have to be consistent with the law of conservation of mass, which says that atoms aren't created or destroyed in chemical reactions.
Atoms are neither created nor destroyed in chemical reactions.
The products of the reaction have to have the same total number of atoms of each element as the reactants had. Remember, the atoms in the reactants have only been rearranged. No atoms have been added or taken away. Pay attention, this is the law.
Order!
The jury has decided unanimously that the defendant has indeed violated the law of conservation of mass. Guilty as charged. Guilty as charged. Guilty as charged.
I hereby send you to 100 hours of community service, scrubbing graduated cylinders, laboratory sinks, and eye wash stations. Bailiff, wake up and take them away.
Oh, where did I go wrong?
To avoid breaking the law of conservation of mass, you have to learn to balance equations. In chemistry, you will balance equations over and over again. It's one of those things you just have to learn. Lots of the calculations we'll do later depend on information you have to get from a balanced equation. When your chem prof asks you to do these calculations, he or she might give you the balanced equation. But your prof might just give you an unbalanced equation and expect you to balance it. So always look at the equations you're given to make sure they're balanced. If your equation's not balanced, the rest of your calculation will be messed up. So learn to balance those equations. We'll help you. Let's look again at the reaction that forms water.
The chemical equation representing the reaction that goes down between hydrogen and oxygen to form water looks like this. 2H2 plus O2 yields 2H2O.
H2 is a molecule with 2 hydrogen atoms, and O2 is a molecule with 2 oxygen atoms. Each water molecule has 2 hydrogen atoms and 1 oxygen atom. The unbalanced equation representing the formation of water is H2 plus O2 yields H2O. This equation is unbalanced because there are 2 hydrogen atoms and 2 oxygen atoms on the left side, but there are 2 hydrogen atoms and only 1 oxygen atom on the right side. One of the oxygen atoms on the right is gone. The law of conservation of mass says that atoms aren't created or destroyed in chemical reactions, so this equation violates the law.
You see, the key to this balancing equations thing is to keep the proportions of the molecules on each side of the equation. O2 consists of 2 oxygen atoms, so we have to make sure both atoms are present and accounted for in the product on the right side of the equation. To balance the number of oxygen atoms on the left side of the equation with the number of oxygen atoms on the right side of the equation, the first step is to place a 2 in front of the product H2O. Now there are 2 oxygen atoms on the left and 2 oxygen atoms on the right. Hey, you're on your way to a balanced equation.
All right, now the oxygen atoms are balanced, but we're not done yet. The hydrogen is still not balanced. There are 2 hydrogen atoms on the left side, but now there are 4 hydrogen atoms on the right side.
Right. Now what?
Just throw a 2 in front of the hydrogen molecule on the left side of the equation. This gives us 2 times 2, or 4 hydrogen atoms, and an equation of 2H2 plus O2 yields 2H2O. We are now within the limits of the law of conservation of mass, because all the stuff is being kept in the same proportions. That's the key.
Here's a harder one. This equation is the reaction between iron and oxygen that forms iron oxide, or rust. The equation says that iron and oxygen combine to yield a compound that has 2 iron atoms and 3 oxygen atoms.
So how will my son balance the atoms on the left with the atoms on the right? Help me rehabilitate him.
Well, ma'am, first he has to figure out how to balance the 2 oxygen atoms on the left with the 3 oxygen atoms on the right. Since both 2 and 3 easily multiply to 6, he can try to get 6 oxygen atoms on each side of the equation. If he puts a 3 in front of the O2 on the left and a 2 in front of the Fe2O3 on the right, then each side will have a total of 6 oxygen atoms. So the oxygen is balanced. Next, he has to balance the iron. Since he added a 2 to the right side, he has a total of 4 atoms on the right. 2 iron units that have 2 atoms each. Now, getting 4 iron molecules on the left side of the equation is easy. He can just put a 4 in front of the Fe. Once again, you see the proportions are the same. If your son does this, he'll be abiding by the law of conservation of mass. Now come up here and explain this to me, son.
Well, sir, the 4 iron atoms on the left side of the equation are represented on the right side of the equation by the 2 iron units which have 2 iron atoms each. And the 3 oxygen units on the left side of the equation, which have a total of 6 oxygen atoms between them, they're represented on the right side of the equation by the 2 compounds with the 3 oxygen atoms each. All atoms are accounted for, so it all balances out, sir.
Good work, son. Section B, atomic and molecular weights.
Of all the elements, hydrogen has the smallest mass and the simplest structure. A hydrogen atom consists of 2 electrically charged particles, the proton, which has a positive charge, and the electron, which has a negative charge. As small as it is, the hydrogen atom has measurable mass. 99.9% of the mass of each atom is contained in the nucleus of the atom, where the protons are. Because as small as protons are, an electron's mass is much, much smaller.
Hydrogen is the first and simplest element in the periodic table. The second element, helium, and all other atoms except hydrogen have another type of particle in the nucleus. The other particle is called a neutron because it's neutral, like Switzerland. It has no charge.
I'm the first element on the periodic table with a neutron. My neutron increases my mass, gives me X-ray vision, and lets me fly at supersonic speed.
The neutrons are in the atom's nucleus along with the protons. The nucleus of every atom has an electrical charge which is determined only by its protons, since neutrons don't have a charge. The neutrons definitely count, though, when you consider mass. The mass of the nucleus includes the combined mass of the protons and neutrons. The combined mass of the nucleus and the electrons is the total atomic mass.
Mass number is the total number of protons and neutrons in the nucleus of an atom. The letter A represents mass number. The atomic number is the number of protons alone in the nucleus. Z is the letter that stands for atomic number.
The total number of protons plus neutrons in the nucleus is the mass number, which we'll represent with the letter A. The number of protons alone in the nucleus is the atomic number, which we'll represent with the letter Z.
There's a general notation to represent the mass number and atomic number for any element. Let's say Q represents any element. Write the mass number of Q as a superscript on the left, and the atomic number of Q as a subscript on the left. Here's what the notation looks like for the element helium, which has a mass number of 4 with 2 protons and 2 neutrons in its nucleus, and an atomic number of 2, which stands for its 2 protons.
Number 6. Number 6.
In the periodic table, the elements are arranged in order of increasing atomic number, which usually matches the order of increasing atomic mass.
The periodic table is arranged in periods and groups. It has 18 main vertical columns called groups and 7 main horizontal rows called periods. This arrangement places elements with similar properties in the same column. The atomic numbers are usually noted above the symbols of the elements. Average atomic masses appear below each symbol. There are 2 general trends in the periodic table. Going down any group, the atoms get larger. Going from left to right across any period, the atoms get smaller. Down larger, right smaller.
Some atoms of an element have different numbers of neutrons in the nucleus than you're led to expect by the periodic table. Such atoms are called isotopes. Take carbon, for example. On the left is carbon with the mass number 12. Using that nifty notation, we can tell that the carbon atom on the left has 6 protons and 6 neutrons, since the atomic number on the bottom tells us that the carbon has 6 protons, and the mass number on the top tells us it has a total of 12 protons plus neutrons. Subtract the number of protons from the mass number, and you will know how many neutrons are in the atom's nucleus. In this case, there are 6. The carbon isotope on the right also has 6 protons, of course, but since the mass number is 14, we know that there must be 8 neutrons in this atom's nucleus instead of just 6. So carbon-14 is a carbon isotope.
Atomic masses are measured in atomic mass units called AMUs. See, we measure atomic mass with AMUs, so we'll have a standard of reference. Some ancient colleagues of mine decided to make carbon-12 the standard, so they assigned carbon-12 a mass of 12 AMUs. That means that an AMU has a mass equal to 1/12 of a carbon-12 atom. See, measuring the mass of atoms with AMUs keeps the measurement darn close to the mass number, which is A. So all masses measured in AMUs are relative to the mass of carbon-12.
It's like referencing the distance of Chicago, New York, and Los Angeles by their distance from Washington, D.C. Washington, D.C. is the standard reference point, and the other cities are measured from that point.
So carbon-12 is the standard reference point for the mass of atoms, and the masses of all atoms are measured from the standard set by carbon-12.
Warning, beware of hazardous terms. AMUs are sometimes referred to as Daltons. If you see the term Dalton, don't panic. Handle the Dalton the same way you would handle an AMU.
Deciding which college to attend is an important choice in your life. You want one that has it all. Here at Atomic Mass University, we provide the smallest particles in the universe with an expansive education at an affordable price. AMU, founded a nanosecond after the Big Bang, is located just outside the nucleus on a pastoral 10 to the 23rd acre campus.
Okay, so you know some elements have several isotopes. Using AMUs, we can calculate the average mass of the isotopes of an element. Why would we do that? Well, because there's a good chance you'll have to do it on a test. Besides, the mass in AMUs listed for each element in the periodic table is actually the average mass of the isotopes of the element. It's the mass of the hypothetical average atom for each element. We'll show you how to figure out the average mass in AMUs as it's listed in the periodic table.
Don't worry though, it's easy. You need to know the atomic mass of each isotope. You can look that up in your textbook. And you need to know a thing called the natural abundance of the isotopes. Natural abundance describes how much there is of a particular isotope in comparison to other isotopes of the same atom. For example,
of all the hydrogen in the world, 99.985% of it is the hydrogen isotope with no neutrons. It's pretty much just a proton. So, 99.985% is the natural abundance of the hydrogen isotope with no neutrons.
You can look up the natural abundance of an isotope in your chemistry textbook. Then, a quick calculation gets you the average mass of the isotopes. We'll show you how.
We'll use two of hydrogen's isotopes to show you how to calculate average mass. Find average mass by multiplying the natural abundance of each isotope by its atomic mass. Then, add the contributions of each together. Again, you can find the natural abundance and atomic mass listed in a general chemistry book. So, here we go. The hydrogen isotope with no neutrons has a natural abundance of 99.985%. And the isotope with one neutron, called deuterium, has a natural abundance of 0.015%. The mass of the first isotope is 1.00783 AMUs, and for deuterium, 2.01410 AMUs. Multiply the mass of each isotope by its natural abundance. Notice that when we're dealing with natural abundance, we have to slide our decimal 2 places to the left since they're really percentages. Now, we add the two products together. The result is 1.0080 AMUs, the average atomic mass of the hydrogen isotopes.
AMUs and isotopes, balanced equations, and the unit factor method are all the things you'll need to understand later when the calculations and the concepts get a little harder.
Stoichiometry deals with the quantities of stuff in chemical reactions. We use stoichiometry to answer the question, how much? A chemical equation is a shorthand way to describe a reaction, giving the formulas for all the reactants and the products. Chemical equations have to be consistent with the law of conservation of mass, which says that atoms are not created or destroyed in chemical reactions. To avoid breaking the law of conservation of mass, you have to learn how to balance equations. Atoms are made up of protons, which have a positive charge, neutrons, which have no charge, and electrons, which have a negative charge. Protons and neutrons reside in the nucleus of an atom. The number of protons in an atom is called the atomic number, and the total number of protons and neutrons in an atom's nucleus is called the mass number. An isotope is an atom that has a different number of neutrons than you're led to expect by the periodic table.
Section C, moles.
First, a little context. Atoms and molecules are so extremely, unbelievably small that even the tiniest samples of matter contain unfathomably large numbers of atoms or molecules. To handle those tremendous numbers, chemists use a weird-sounding unit of measurement called the mole. A mole is a unit of measurement that represents 6.022 times 10 to the 23rd things. Yes, things. Moles are designed to measure atoms, molecules, ions, electrons, sesame seeds, or tiny things like that. But if you wanted to, you could talk about a mole of beer nuts. Of course, a mole of beer nuts would cover the entire surface of the earth. Think of the term mole like the term dozen. You know that a dozen refers to 12 things. 12 eggs, 12 donuts, whatever. A mole refers to 6.022 times 10 to the 23rd eggs or donuts or atoms or molecules, whatever you're measuring. The magic mole number, 6.022 times 10 to the 23rd, is also known as Avogadro's constant. Not to be mistaken for avocado's constant, which is really just a recipe for guacamole.
How many particles are in a mole? 6.022 times 10 to the 23rd power.
So the mole, like scientific notation, makes it easier to deal with humongous, unwieldy numbers. A mole of moles, for example, would be more than 60 million billion moles.
So the mole is basically just a way of keeping up with huge amounts. 1 mole of atoms has 6.022 times 10 to the 23rd atoms. And if you have 1 mole of water molecules, you'd have 6.022 times 10 to the 23rd molecules. This is tricky, so listen closely. In that mole of water molecules, you'd have 3 moles of atoms, since each water molecule consists of 3 atoms, 2 hydrogens and 1 oxygen. In 1 mole of water molecules, there's 1 mole of oxygen atoms and 2 moles of hydrogen atoms.
And here's another cool thing about moles, right? 1 mole of any type of atom has a mass in grams equal to the atom's atomic mass measured in AMUs. Pretty cool.
When you look up the atomic mass of carbon in the periodic table and see that its atomic mass is 12.01 AMUs, you know instantly that 1 mole of carbon atoms weighs 12.01 grams. You look up iron, Fe, and see its atomic mass is 55.847 AMUs, you know that 1 mole of iron atoms weighs 55.85 grams.
It's that easy, which is a good thing, because you will have to use this conversion constantly as you convert back and forth between moles and grams.
Replay! The gas xenon has an atomic mass of 130.30 AMUs, so a mole of xenon atoms weighs 130.30 grams.
Now let's talk about molecular mass and molar mass. Molecular mass is the combined mass of a group of atoms forming a single molecule. Add up the masses and AMUs of the atoms forming the molecule, and you have the molecular mass.
Molar mass equals the mass of 1 mole of a substance. Molar mass is the mass of 1 mole of a single type of atom. If the substance you're measuring consists of molecules, the molar mass is the mass of 1 mole of the molecules.
When you do calculations, you'll usually measure both molecular mass and molar mass in grams per mole, which is how many grams 1 mole of whatever substance you're using would weigh. For instance, when you read that the molecular weight of carbon dioxide, CO2, is 44.01 grams per mole, it means if you had a mole of these carbon dioxide molecules, it would weigh 44.01 grams.
Now, if we want to, we can express the weight of a single molecule. To do that, we use AMUs rather than grams per mole. We'll do an example showing you how to find the molecular weight of carbon dioxide, which we've already told you is 44.01 AMUs. Then we'll convert our answer to grams per mole.
So let's find the molecular mass of carbon dioxide in AMUs. Molecular mass equals the sum of the masses of the atoms in the molecule. So the first thing we have to do is look up the masses of the molecule's component atoms in the periodic table. Carbon has a mass of 12.01 AMUs, and oxygen has a mass of 16.00 AMUs.
CO2 is made of 1 carbon atom and 2 oxygen atoms, so the mass of 1 molecule of carbon dioxide equals the mass of 1 carbon atom plus the mass of 2 oxygen atoms. According to the periodic table, the mass of carbon is 12.01 AMUs, and the mass of oxygen is 16.00 AMUs. 1 times 12.01 AMUs plus 2 times 16.00 AMUs equals 12.01 AMUs plus 32.00 AMUs. That gives us 44.01 AMUs. But like we said, you won't use molecular weight in AMUs very often. Most of the time, you'll need to express the weight of a single molecule in grams per mole. So we'll make that conversion now. It's the easiest conversion you'll ever have to deal with.
Hey, to convert from AMUs to grams per mole, you literally just change the units from AMUs to grams per mole. We'll show you.
Since 1 mole of any type of atom has a mass in grams equal to the atom's mass measured in AMUs, the numbers don't change when you convert your units to grams per mole. Here's the calculation of the molecular weight of carbon dioxide again, this time using grams per mole instead of AMUs. Notice that it looks exactly the same as the calculation we did earlier using AMUs. We've just written in the units grams per mole, where earlier we had AMUs.